All right, let's give everyone just a few moments to drop on in. Everyone is doing well on this fantastic Friday. Oh, I suppose that's enough time. All right, let's get this show on the road. Greetings, tech artists from around the world. It is Friday. It is 12:30. It is time for Tech Art Talk Live. My name is Chris, and I'm going to be your host for today's session. Last week, we started diving into the perplexities that is shader writing. And hopefully you were attending last week and you realized, okay, this shader writing, this HLSL, really isn't such bad stuff. We didn't do a whole lot, but we got things going. When we used a program called Shader Ed, which is it's an open shareware software that you can use and you can download and you can use it for your own projects, and that's what we're going to be using here. It's not necessarily my favorite, and I'm still learning with it, but it's still a good enough package to kind of get the job done. We're going to continue all that this week, and we're going to focus on how to do texture maps in shader languages. And you're probably going, well, geez, isn't it you just go and you select the image and it just does it for you, right? Well, kind of, sort of. Well, there's actually a lot of stuff going on behind the curtain, and we're about to expose that curtain today and show you what all is actually going on. And we're going to show that through doing it in HLSL. All right, so let's get things started here with the presentation. All right, texture mapping. It is a bit more work than that's expected, but it's not too much work, actually. It's not so bad. All right, now I'm kind of assuming that if you've gotten this far in your career and you're actually watching this video, that means you kind of have an idea of what texture mapping is. And just to give you the kind of like Cliff Notes 5,000 foot version, texture map coordinates are provided on every vertex. And they're two-dimensional, and what they usually go is between 0, 1 in kind of a horizontal and a vertical direction, or in what's called the U and the V directions. Anyway, because it corresponds to a two-dimensional image, you can use those texture coordinates to look up their corresponding values from an actual texture image. Now, it doesn't have to come from a texture image, it can come from anywhere, but we're just kind of keeping it simple and using coordinates, using texture images right now. All right, here's an example of what we are looking at here. In DirectX or HLSL, you'll notice that the coordinates kind of go from across from left to right in the U direction, and it goes from value 0 to 1. And so all of the little texture values in here are somewhere between 0 and 1. And V corresponds to the vertical direction, and those go also from 0 to 1. Notice here that this is actually very important when dealing with HLSL. The origin, or the 0, 0 point, is at the top right or top left corner. When dealing with GLSL, it's right in the center of the image. Which one is better? Well, honestly, they're both about the same. It's just that it depends on the context of what you're actually building, and you might have to make some adjustments along the way. Okay, now here's a little demonstration of the texture mapping concept. So here we have the coordinates on a polygonal face. And you'll see that because they go from 0 to 1 and then 0 to 1 in the U and the V directions, that also corresponds to a two-dimensional texture map. And so these points get mapped on to the polygon pixel by pixel corresponding to the values of the texture map, and the texture coordinates get interpolated on the pixels between these two vertices, and the UV values that get interpolated correspond to the equivalent values in the texture map, and then you end up, it looks like the image has just been pasted right on top there. All right, on this terrible image, if you look at here, we got a 3D object and you have a texture map. The texture map just kind of wraps around the whole thing. It's kind of like it's one of those little chocolate balls that you get at Christmas, and it's wrapped up in aluminum foil. So if you were to unwrap that aluminum foil, then that would be, of course, the texture map going around the chocolate ball, which is your geometry. All right, so with that brief introduction, let's get things rolling as far as programming in HLSL is concerned. All right, we're going to start with a brand new project. This is just a little preview of what you're going to be looking at here, of what we're going to be achieving in today's session. So I'm going to go into Shader Ed. I'm going to go to File, New, Empty Project. And with that going, we are ready to rock and roll. So I'm going to go ahead and go right off and save this as, and I'm going to go on to my location, TechArt EDU, and this is TechArtist Talk, and we are on the 52nd week. Can you believe it already? And so we're going to create a brand new one called, let's call this TM Demo. That stands for Texture Map Demo. I'm going to go ahead and save. All right, we've got that going here. And so when we are working in Shader Ed, we do everything with shader passes. So let's go ahead and create a shader pass. Go to Project, Create, Shader Pass, and then let's provide a name for it. Let's call it just Texture Mapping. And then change the language from GLSL to HLSL. And leave the vertex shader path and the pixel shader path the same, but we're going to change the name of our vertex shader entry and pixel shader entry. So the vertex shader entry is going to be just vertex underscore shader. And pixel is going to be pixel underscore shader. All right, nothing too complicated there. And we're going to leave the rest of the parameters here as default. Click OK. And now notice that we have two bits of code up here. The pixel shader, which is called, the pixel shader, and then the vertex shader. Oh, and before we get started here, we're going to need some geometry to work on. So I'm going to add this geometry. I'm going to right-click my texture mapping shader pass, and I'm going to add some geometry. And I'm just going to add a cube, and let's see, we're going to call this my box. Okay, and just that. Now we don't see anything yet in our preview window, and that's because we need to actually give the shader something to actually look for and grab onto, because otherwise it won't be able to tell. Oops. We got a little bit of a preview on that. There we go. All right, now we're going to work on is, we're going to start with the vertex shader. So wherever it sees that it says texture mapping VS, we're going to start with that. Now, one thing we didn't go into last week is we didn't go over comments. And when you're dealing with HLSL, there are two types of comments. There's the single line comment, which is right here, and you'll notice that it's forward by two forward slashes by that, and we're going to call this a single line comment. All right, and the alternative of that is a multi-line comment, and the multi-line comment is delimited by a slash and a, let's see, yeah, it's delimited by a slash and a thing. Okay, we are not viewing the thing here. So let me see if this right. Yeah, there we go. We're looking at that. Now we're looking at it. Now we're broadcasting the right thing. Okay, apologize for that. If you didn't see that before, what we did was we created we go to project project, go to create shader pass, and then we created a shader pass. We entered in all the parameters, and then when we did texture mapping, we right clicked on that, add a geometry, and then we created our box. And so here's our first entry into our vertex shader. We call it the vertex shader because it's got the VS hanging out right here. But on the single line comment, oh, we're going to see that again. All right, now the multi-line comment is delimited by a / and by a star, and I'll say this is a multi-line comment. Not that it really matters, but we've delimited by a star and then a /. And so that is how we create our comments. Nice and simple. This is how everything goes. All right. Now the next thing we have to worry about is things called resources. And in order to help us deal with our resources, we're going to take advantage of something that, if you're familiar with C and C++, you'll know that there is a kind of like a little pseudo sublanguage that it complements the C and the C++ and the HLSL called a preprocessor commands. And the preprocessor commands deal with things like define, if, then, else, or include, and we're no exception. So what we're going to do is we're going to add in some resources here. And so we're going to add the resources here, and I'm going to call this, I'm going to go /, and I'm going to add a little line here. So we go resources, kind of make it look like, and then so here it is, #define flip texture y. Now notice that this comment here is a global, this is a global variable, and so basically it's an association. Wherever the preprocessor or the precompiler finds the word flip texture, it's just going to replace whatever is here inside of the compilation. And so this is a way of making things simpler. All right, and so what we have to do is we've got this global variable already taken care of. So let's go ahead and create some actual variables that we want the user to actually interact with. And we're going to create the world matrix, the view matrix, and the projection matrix. The world matrix are the transformations that the user puts onto an object as they're moving it through the world. The view matrix is moving the entire world so that it corresponds, so that the camera is looking down the negative z-axis. And the projection matrix is the matrix that applies the depth pyramid or the perspective cone onto it, and it turns everything into a flat area. And so we need these three matrices to be installed here. Now we have to add these. So because they are new variables here, let's go ahead and add them to our shader pass. So I'm going to right click on texture mapping here, and then I'm going to choose the variables component here, and oh, it's not there yet. Okay, it's not there yet because I forgot to save it. I'm going to go ahead and save, and it should be ready to rock and roll. So now if I click on here and go to variables, and there we have all of our matrices. So we want the world matrix to be a geometric transformation matrix because that's what's going on here. Our view matrix is the view matrix, and the projection matrix is the projection. So that's all pretty much nailed on here, so we are good to go with that. Okay, just a little quick save, and then we are off on our own. Okay, remember how I said that you can use some of these preprocessor commands in order to kind of make things simple? Well, we are going to create a convenience function for ourselves that is going to help us align our textures. Remember that for HLSL, the upper left-hand corner corresponds to the origin. And so what we're going to do is we're going to create a little helper function to kind of help us with that in case something needs to be going on, in case something needs to be adjusted. Okay, so what we have here is we're creating a brand new function, and it's going to return a float 2. So in other words, it's going to return two coordinates, in this case a u and a v, and we're going to call our function get underscore corrected underscore texture underscore coordinates. And the input for that is going to be another float 2, which are just some kind of a pair of UV texture coordinates. And now here comes the in-processor thing. So when the preprocessor sees this flip texture y, what it does is it inserts code. What it inserts it with a little bit of logic. So if it sees this flip texture code, then it inserts this amount of code where it says return float texture coordinate dot x and then 1 minus texture coordinate dot y. So that means if our shader engine is doing things a little bit uniquely and we need to flip our texture, well then what this function is going to do is just simply flip our texture by just creating the inverse of our y value. Remember, y, it corresponds to v, and it goes between the values of 0 and 1. When we subtract 1 from that, we're basically flipping it or taking the inverse of it. Now if flip texture y doesn't exist or equals 0, then we're just going to return just the plain texture coordinates as we receive them. Okay, so let's create our texture data structures that we're going to be using for this project. Okay, here are now notice that these are our Vertex shader data structures. They're not for both the Vertex shader and the pixel shader, is just for the Vertex shader. And so the first one is our VS input struct. And input, we're going to take in a float 4, which is going to be the object position. And notice that it has a colon here with the word position. Position, as a reminder, is what's called a semantic. And the semantic is a clue to tell the rendering engine what to do with this particular variable. Some of them are necessary, some of them are for, more or less documenting, and others are very important purposes. Now, in this case, the position, the normal, and the position and the normal are kind of important. The word text coordinate here that we have for our texture coordinate, it's necessary in order to make this demonstration because it's about texture mapping, but it's not absolutely essential for this. So this semantic is not essential. And we're looking for the normal here, and we will need the normal because we're going to need it in order to render with our textures. So we've got our object position, I've got a float 3 normal, and our float 2 for our texture coordinate. Now for the output from our Vertex shader, all we need is a float 4, and yes, where it says colon SV position, you do need to have this SV position. Because if you don't have this SV position, then the shader is going to look at you and it's going to go, what's going on here, bub? I don't understand what's going on. All right, float 2 means we're going to create our texture coordinates and we're going to take them and modify and possibly massage our texture coordinates inside of the context of the Vertex shader. Now this is strange. Now this is a peculiar thing with shader ed. Normally I wouldn't teach about the normal right now, but right now shader ed, as far as I'm aware, must have a normal in it in order to get texture mapping working. Why? I don't know. This is something to figure out in the future. So this is why we're including it in the Vertex shader input structure. All right, so let's create our Vertex shader now. Okay, here is our Vertex shader. As our return data, we want it to be a VS output struct. Here's the name of our shader, and it's called Texture Vertex Shader. Now, did I save that correctly? I'm going to go ahead and check my properties here. And, I spelled it incorrectly. So I have this. So I call this Vertex Shader. So let's change this name to match what's here, because I like this one just a little bit better. I'm going to change this one to this one. And then I'm going to change this one to Vertex Pixel Shader, because I know I'm going to have to do that in just a little bit anyway. Okay, so I'm going to go ahead and save all this so everything is running well. All right, so we have the name of our vertex shader. It's called texture vertex shader, and the input to that is our VS input struct. Okay, and the first step is to take our VS output structure, and we're going to create an empty variable for it. And so in order to do that, what we're going to do is return a brand new VS output structure, and then we're going to cast 0 to it. Then what we're going to do is the most essential portion of a vertex shader, and that is to transform all of the vertices from local space into world view projection space. And so we're going to do that by multiplying in.object position, which is the position. We're going to multiply it first by the world matrix. Then we're going to take that result, multiply it by the view matrix. And then we're going to take that result and then multiply it by the projection matrix. And that will get all of the coordinates in where they're supposed to be. Now, speaking of coordinates, let's deal with those texture coordinates. Now, I'm going to say my out.texture coordinates, and we're going to call our little helper function get corrected texture coordinates for in.texture coordinates. So basically, we're just going to send our little helper function our texture coordinates to say, okay, if you've got it, then deal with it. And so this little helper function is going to do some heavy lifting for us. All right, hit save, and yes, it compiled, and there were no errors, so everything needs to be good. All right, the rest of this needs to be done inside of the pixel shader. Now the vertex shader kind of like, other than the utility function and these kind of like extra variables and so forth, there's really not too much new stuff going on here, except where we're passing through the texture coordinate. So let's take a look of now what goes into the pixel shader. Click that over, pixel shader. All right. So like the vertex shader, the pixel shader has got to have some resources. And so what we're going to do is add some structured data for our pixel shader. All right, so here are our pixel shader resources, and we're going to create a new input called PS input struct. And this structure pretty much has to match the exact same structure that's coming out of the vertex. So notice that they're called two different things. Coming out of the vertex shader, it's called a VS output, but coming into the pixel shader, it's called a PS input. Now notice that they contain the exact same objects in the exact same order. And what we're looking for is a float 4 position. And notice that it's called SV position. This is important. This has got to be placed. And it has a UV texture coordinate. All right. So let's see. All right. So I'm going to move this over into here. And move that over there. And move this forward by a couple of slides. All right. Okay. Now that we've got this going here, I'm going to go back to my lecture here and talk about whenever you're using textures, you've got to do 3 steps. And now, it's a similar process when doing GLSL. So HLSL is pretty much going to be the same. So the first step is you've got to declare a texture object. So that texture object has to be in your code. You've got to go and create a texture object. Then you've got to declare and initialize something called a texture sampler. A texture sampler tells you how to sample in your textures because there's a bunch of different ways of sampling in your texture, and we'll go into that a little bit later. And then the third step is you've got to sample your texture using the declared, you got to sample your texture from your texture object using the declared sampler. Okay, those are the 3 things that you've got to look out for. Okay, so let's go back to our demonstration. So let's declare our texture object. Okay, so let's see, I did a goof. So let's see, what is it? What is the word for this? In my notes, I know I did this wrong. So let's see what this value is. So it's I think it's called texture object. Is that the right name for it? No, it is not. What is the name for it? Oh, you would think I would remember this by now, but I'm going to cheat and I am going to look ahead and see what that name of that object is. Oh, it's called a texture 2D. Okay, so that's what it's called. And I should have known better, but let's see. Texture mapping, I go edit code, all right. So here we go back into this as a called a texture 2D. All right, yeah, we got it blue now, so that means it's doing it correctly. And we're going to call this, what are we gonna call this? Let's call it just texture map. All right, good. We've got that going. And I hit Control S, so everything is going fine, so nothing is problematic. Now we've defined our texture object. Let's go ahead and define our texture sampler. Okay, here's our texture sampler, and we're going to first declare it as a sampler state. Now this is very important. It's got to be done this way as a sampler state. And that means that since we declare it this way, it's got to declare the name, and then inside curly brackets we're going to put all the parameters. Now notice that it's an open curly bracket, and then we have these words. It says filter equals min, mag, mip, linear, and then address u, and then address v, and then we're going to terminate our curly bracket, and we're going to go colon register as 0. Okay, that is just a little bit of a semantic for shader ed for the user to know, okay, we're going to be using the S1 or the S0 or the very first sampler state, and this is where it's going to be called. So this is a little bit of a semantic here to identify that this is going to be a sampler state, and so they would call it S0. Now notice that the filter, the address U, and the address V, we're going to leave that alone for now, and we're going to come back to that in just a little bit here. And I want to be a little bit thorough, and I'm going to add some comments to here. I'm going to call this our texture object. All right, we've got our texture object going. And now let's create our data structure. Oh, we already have our information. So yeah, we already have our data structure here. So let's go ahead and create our pixel shader. Look at that. I copied the wrong thing in my notes. What was I smoking? I must have been smoking some pretty serious crack at the time. I tell you. But not to fear. We have everything loaded up ahead of time. Oops. Oh, and I crashed shader ed. Very cool. That's always good to know. All right, this is going really awesome today. All right, let's load this in here. I'm going to open my TM project, and then I'm going to grab my pixel shader. There, it's not very complicated. And then I'm going to go back to my project, and let's see, this PC, it's on the F drive, and it's on the TechArt EDU, TechArtist Talk, texture mapping, tdemo, open. All right, I'm going to go in and open up all of my shaders. And so here it is. So let's go ahead and plop this down for our pixel shader. Notice that our pixel shader here is brutally simple. All right, we have the texture pixel sample, the pixel shader is the name of our function. We're going to return a float 4, which means we're going to returning red, green, blue, and alpha. And then so the input is for the PS input We're just going to call it in. Now notice that that is directly coming out from the Vertex shader. So we have kind of like an invisible pipeline from our Vertex shader to our pixel shader. And then we finish this off with a semantic called SV target. Now this semantic is necessary because this identifies to the rendering engine that this, yes sirree Bob, is our pixel shader. And so here's the third step, where we're actually going to be just returning a sampling of our texture map. And we're going to go to that. Okay, we're going to go color texture. Oh, I didn't call it color, I call it color texture here. So let's call this texture map. Texture map.sample, and then color sampler is the instructions on how to sample our object. Okay, I'm going to go ahead and save this. And everything is fine, but we still don't see anything. Why? Because we don't have an actual texture yet. And so what we have to do is we have to pull in a texture to this. And so what we do this, we go over into objects, and I'm going to right click on object here. I'm going to right click in there and I'll say create texture. And then I already have, let's see, this PC, go into F, go into TechArt.edu, and TATAL. Okay, look at all of those TechArtist talks. Here we go for that. And then we are going to go for this decal. I'm going to open that. And then I'm going to right click it, and there it is. And so we have to bind it to the project, and we want to bind this particular texture to our texture mapping project. Up, and there it is. Okay, everything looks kind of good, but there's a slight problem. Everything is upside down. Okay, remember how I mentioned that there could be a problem with this because I'm just learning shader ed myself. And that means is that shader ed does something funky with HLSL, and it flips the texture coordinates. So what I'm going to do is go back into the Vertex shader, and notice here that I have a little flag here where it says flip texture Y. I'm going to go ahead and change that where it used to be 1. I'm going to make that 0, and then when I go ahead and save this, it flips everything correspondingly correct. And so what we've done is for every polygon here, we've put the little decal on here, and we are good to go. And so that is where we are pushing things towards. All right, so that is about the extent of the coding that I wanted to go over today, but I wanted to go over what some of the nuances and some of the essence of what this color sampler is, because really this is where all the magic happens, is in the color sampler here. And I'm going to go ahead and load that up here. And let me go ahead and grab all this stuff. All right. All right, so we're almost there. All right, so we got what we need. Okay, so let's get into the swing of things. All right, so when you're dealing with texture maps, the texture maps are broken up into things, little pixels, but they're not actually called pixels. What they're called is texels. And so what we have to do is we have to map our texels onto the pixels onto the screen. Now sometimes our texels might be larger than our actual pixels. So therefore what we have to do is we have to change and kind of magnify our pixels in order to match their texels on there. And so that's called magnification. Now also what happens is when the pixels are covering up more than one texel, then what we have to do is minify or make the texels a little bit smaller in order to fit onto the pixels. And so that is the process called minification. So a lot of times what we're dealing with is magnification and minification. And here's a little graphic of that, of where we're magnifying things. We have our portion of the texel, or we have our portion of the pixel, and then what we're going to do is then blow that up in order to magnify it to fit within our texel. And here's where an example of minification is, where we have our pixel and we see that it's larger than the actual texels. And so what we have to do is reduce its scale into a shape that fits the texel scale 1:1. Okay, so there are three ways of doing this texture magnification. And there are three mathematical principles, and we're not going to go into the math. I'm just going to describe what these functions are. There's point filtering, linear interpolation, and anisotropic filtering. Okay, let me explain the three. Okay, point filtering uses the texel colors closest to the pixel center. And so what this does is says, okay, where's the pixel center? And then we use the texel color that is closest to that pixel center. And this is kind of produces a kind of blocky, kind of like an old Doom Duke Nukem look, you know, from heralding from the mid 1990s. And this is a very, very fast technique, and it works very well. And it works great and it's fast, but it does produce little blocky results. Now what looks a little bit better, what is a little bit slower, is called linear interpolation. So what we're going to use is bilinear interpolation in order to figure out what texels to use. So what we do is we have the center of the pixel, wherever that is, and then we're going to use that center of that pixel to interpolate between the upper two texels. We're going to interpolate however that far is, and then we're going to do the lower two texels. And then depending on the height of the pixel in between the two texels, we are going to interpolate vertically in between there. So we're going to do 3 interpolations, 2 across horizontally and 1 vertically. And that's going to produce a linear interpolation. This looks much better and it's much smoother. However, it is slower because we're doing 3 linear interpolations. Now the third one is called anisotropic filtering, and this is good for objects that are oblique to the camera. So what that means is normally the polygons are going to face the camera. But what happens if it's kind of like at an angle? Then that produces some kind of weird, funky results, and it creates some distortion. And so the anisotropic filter kind of fixes that. And so the anisotropic filter is the most expensive, but it's going to produce the best looking results. So it produces kind of like texture maps that look kind of like this, where one here is where this kind of like has been pushed off into the distance and it kind of looks funky and it kind of like goes crazy and blurry. But here's with anisotropic filtering and it looks much sharper. Now that was texture magnification, but what about texture minification? Well, then we got to do the same thing, but kind of the opposite direction. It's a little bit more complicated. We could just ignore the texels but that are being obscured, but that's going to produce artifacts and it's going to decrease the rendering quality. So it's going to make it look chunky and there's going to look like there's holes in the way. So we don't want to do that. And so what we want to do is downsample the image. And this is where the concept of MIP mapping comes in. And MIP mapping is something that happens whenever you load a texture map into your texture engine. And you didn't even know about it all the time. You just said, hey man, I got my my JPEG or I got my PNG. I'm going to load this up into the Okay, why do you have to load it up into the engine? Because the engine has to pre-process your texture map and do the MIP mapping on it. You're probably going, well, what's MIP mapping? Well, when it creates a new texture image, along with the texture image, it creates duplicates of the texture image. And so each duplicate is going to be 1/2 the size of the prior texture image. So what we have here is the full-blown texture image. We're going to take half the size of that, which is actually just 1/4 of the size, half in X, or half in U, half in V. We're going to get another 1/4 of that, and then 1/4 of that, and 1/4 of that. We're going to keep going until the last sub-pixel or the sub-map is only just 1 texel large. And so what does this actually look like inside of the engine? Well, then your texture maps, instead of going from a general regular texture map, tend to look like something like this, where we have the full-blown one is 1/4 as much, this is 1/4, and then all the way down to the 1 texel size MIP map. Okay, that is what's going on behind the scenes. I bet you didn't know that this was actually happening but some of you may have. Who knew? But anyway, this is what everything needs to be pre-processed when it goes into the engine. Okay, so now we have to figure out, how do we evaluate which MIP map to use? Do we use a larger MIP map, or do we use a smaller MIP map? Because most probably the pixel value is going to lie somewhere in between. Okay, so we have, once again, two different techniques for doing our MIP mapping evaluation. We have point filtering, which is the exact same algorithm, is that it takes whatever MIP level is closest to the pixel center. Either use the upper one or the lower one. And that's very sad. Or it'll use linear filtering, which selects the two surrounding MIP maps, the upper one and the lower one, and then it blends in between the two. It does a lerp in between the two, depending on which the pixel map is actually closest to. And then it does this, and it does use anisotropic filtering as well. So anisotropic does actually work. So you have to choose what kind of MIP mapping that you want. Either point MIP mapping, linear MIP mapping, or anisotropic filtering. Okay, when we go and create our sampler state inside of our code, what we have to do is look at we actually create these enumerations, because there's only so many ways that we can combine these things. And so one could be like min, mag, MIP, point, and so forth. And so forth, where you have min, mag, MIP, linear, anisotropic, and that means it's done for all three. Done for the minification, the magnification, and the MIPPing. Or you can mix them up, and this is the minification and the magnification are point, but the MIPPing is done linearly. It just goes on and on. So this is what this word means when we say filter inside of our sampler state. This tells the rendering engine what filters to apply when either doing a magnification, a minification, or a MIPPing in between hand. So what about these last two words where we have address U and address B? Okay, let's get on to those. Okay, so these are addressing modes, and so this tells the rendering engine what to do when the texture samples are outside of 0 to 1. Remember how I said that the textures actually go from the point value of 0 to 1? But what happens if they don't? Well then, this is actually a super powerful technique that is used for visual effects. Remember we were talking about rotators and panners? Well, panners are actually taking the texture coordinates and adding values to it to go beyond that 0 to 1 range. And there are 4 variables, or 4 addressing modes that we can deal with. It's wrap mode, mirror mode, clamp mode, or border. Wrap mode actually just keeps duplicating it around. So it just keeps wrapping it horizontally and it keeps wrapping it vertically depending on the number of the texture coordinates. Now, if we wanted to make it larger, we would decrease our texture coordinate size, and depending on how many times this loops into it, we would get these number of duplications. And so that's wrap mode. Now, the complement of that is to mirror mode. Now, it's kind of like wrap mode, but the mirror of it kind of like mirrors from left to right and up and down. And so what this does is this help reduce some of the seaming that might happen if your texture map itself isn't necessarily very good looking and you want to get rid of the seams. Well, mirroring can help get rid of the seams. Then we also have clamping. Clamping takes the pixel values of the texture map of the far left edge and the bottom edge, and whatever those colors are, it just stretches them right across. And so that's really all it's doing. It's just taking the last pixel color values and then stretching them across horizontally and vertically. And so that's clamping. And the last one is border. Bordering is a way of saying like, okay, I don't want to do any of that. I just want the background set, or I just want the thing set. If it's not fitting within my texture space between 0 and 1 properly, I just want to leave it in there. So let's go ahead and see what some of this stuff looks like in action here. Now, I found here, though this is kind of strange, shader ed does not, it accepts these parameters, for filter, the address U and the address V, but it overrides them. Who knew? And so what I could do is, if you go into your texture object, right click it and go to properties, there you see our parameters right there, where we have our minification filter. And if we look for our minification, we should get 3 values. Okay, here we have the nearest, or we can go nearest corresponds to point. Linear is linear interpolation. And then here, if we're dealing with mipping, we're going to the nearest mip map nearest, linear nip map nearest. Oh my gosh. And so that's a combination of point. And so instead of actually creating an enumeration right in here, they actually wrote it all out in here. Now magnification, remember, is a little bit easier. And so all we have to do is do nearest and linear. Now notice that Shader Ed does not support anisotropic filtering. Why? I do not know. I just found that out. So what was going on here? And now here we have our wrapping, S and then T, or what that's also called for wrapping U or wrapping V, or wrapping vertically, wrapping horizontally, or wrapping X or wrapping Y. So notice this is called repeat, and it does repeat. And then here it is mirrored repeat. And we have the last is clamp to edge. Notice it doesn't do the border, which is the fourth way of mode, the fourth mode for sampling this. So what would this actually look like? So I'm going to go into the Vertex shader, and I am just going to multiply my texture coordinates by 4 to kind of give it a little bit more. So I'm going to go my in.texture coordinates. I'm going to go 4 times, and then notice that, ooh, look at that. This does it, but we have got clamp on here. So I'm going to change this back to repeat. And so there is 4 by 4. So that's a little bit hard to see. Yeah, so, but let's go 3 by 3. So I'm going to go 3 times. And so our texture coordinates are repeated 3 times. Okay, so we're not going to see much of a difference changing the sampling mode between the minification filter and our magnification filter, just because our texture is too simple. But you'll notice here that if we wanted to go into the wrap mode as far as horizontally is concerned, we can either do a wrap, which is just called repeat. We can do a mirror, which it kind of like modifies the middle one, or we could do clamp, and it just gets the far edge. And we can repeat that along with the vertically, and that is mirrored. There we go. Or that is clamped. Okay, which does the bottom one. Okay, so those are the filters that you have in order to access your texture map, and the modes that you tell your shader how to handle when the texture coordinates go beyond 0 and 1. And that shows it how to do it. Okay, that pretty much wraps what I wanted to cover as far as today's lecture is concerned. I hope that you're able to do that. And so I'm going to fast forward on to my slides here. And just as a reminder to everyone, I'm going to make sure to come to the Houdini Secrets Houdini Users Group meeting tonight, and that is going to be at 7 o'clock. And if you want admission to that process, or come to the Houdini Users meeting tonight, go to the meetup and look up the OHUG. That's OHUG, OHUG, and it will take you to the page. Go ahead and register for OHUG meeting number 10, I think we're at. And then it'll give you the Zoom link, and you can come and join us. And I hope you do join us, because we have David Santiago, who is one of the lead technical artists over at Insomniac, and he just finished with his magnum opus of Ratchet and Clank for the PS5, which he followed up with a lecture over at the GDC, which just finished up a couple weeks ago. All right, so I hope you enjoyed what we talked about today. So if you have an opportunity, check in Tech Art Talk Live next week, and that's going to be the 13th of August, and then we're going to talk about some real 3D shading part 1. We're going to go over the basics of Phong shading. So that's going to be the fundamentals in there. So I think it's just going to be just one lecture on that, or it's going to be part 1. So this is going to it's going to take a couple of lectures to actually go through it all, but part 1 is going to be next week. Okay, now if you like what you saw today, go ahead and subscribe down in the lower right-hand corner of the window. Go ahead and subscribe to us on YouTube, or my name is Chris Rhoda. Check me out on Facebook and on LinkedIn. And otherwise, go to TechArt.edu, which is the website, so TechArt.edu. And TechArt.edu can also be found on Facebook and on LinkedIn. And otherwise, go check out TechArtEDU.com, which is the website. Once I finish with this book, within the next couple of weeks, I hope, I will start updating again and keep going and get things going. But they have a little opt-in button there, so go ahead, click on the button, opt in, and then we'll send you all stuff when we have it available. Thank you very much for joining me today for Tech Art Talk Live. I enjoyed showing you all about texture mapping in HLSL. Join us again next week where we start dealing with part 1 of 3D shading. Until next week, arrivederci.